Dear students, in this short video, we will see AVL tree. This AVL tree is named after its inventors, Adolphson, Wellesley, and Landis. This is a special type of binary search tree. It is also called dynamic self-balancing tree. When you perform insertion, the insertion in case of binary search tree is based on key. If the key data to be inserted to the BST is greater than the current node, then that node has to be inserted to the right of it. If key to be inserted is less than the current node, parent node, then it has to take left side. Suppose the key to be inserted is existing in the BST. In such case, we have to ignore that one because it is duplicate data. When doing so, we may observe the tree which is in imbalanced state. The imbalancing means either left side is heavy or right side is heavy. This can be determined with the help of balancing factor. By looking to the balancing factor, we can we can balance the tree. The balancing factor can be 0 or can be 1 or it can be minus 1. That is why based on the balancing factor the tree get balanced. That is why it is called dynamic self-balancing binary search tree. Let us take one example. What is that balancing factor? A tree is constructed is a BST because it is where the lower value is in the left side, higher value in the right side. Now we have to find out the height. The balancing factor is computed as the height of left subtree minus height of right subtree. For the external node, the height is 0, so balancing factor is 0. Like in this case, node 5, 11 and 17 are the external because these three nodes are not having children or child node. That is why balancing factor is 0. Now for 8 has two children, 5 and 11. Now we have to compute the balancing factor. The height of left subtree, that is 1. Height of right subtree, that is also 1. The balancing factor is 1 minus 1. So it is 0. 0 is valid. In this case, for 18, the height of left subtree is 1. To reach to this node is 1. There is no right subtree, so it is 0. 1 minus 0 is 1. This value is also valid, allowed value. We'll go for the node 12. The height of left subtree, the height is 2. Height of right subtree, that is also 2. Okay, height of that is 0. Here it is 2. Here it is 2. 2 minus 2 is 0. This is 0. The valid 0 is valid, 1 is valid, like that. So this is a balanced tree. This is a AVL tree. We'll take this example. In this case, 2 is leaf node, 9 is leaf node, 17 is leaf node. The height of that is 0. Height of these three nodes 0. For this node, height of left subtree is 1. Height of right subtree, there is no tree at all left, subtree is not there, so 0, 1 minus 0 is 1. Height of, for this 5, height of left subtree is 2, height of right subtree is 0. 2 minus 0, 2. It is violating because 0, 1 and minus 1 are allowed values, 2 is not valid, not allowed. That is why this particular tree is not AVL tree. So balancing factor can be obtained by subtracting height of right subtree from the height of left subtree. The values allowed are 0 or 1 or minus 1. Any other value if you get, the tree is said to be imbalanced. So as and when you perform insertion, you need to check the balancing factor of that node following. Case 1. After the insertion, the balance factor of each node is either 0 or 1 or minus 1. The tree is said to be balanced. It is a well balanced tree. The searching will be efficient one. The performance is very good in such case. Case 2. After the insertion, the balance factor of at least one node is not 0 or not 1 or not minus 1. The tree is said to be imbalanced. In such case, you have to balance the tree either to the right side or to the left side, either once or twice. That is why it requires either single rotation, right, rotate left or rotate right, or double rotation, once left then right, or once right or to the left side. In this way we can balance the tree get balanced. Now we'll take some specific example, case by case. We'll go for single rotation, that is left rotation. Let us take this example. As you can see, all the nodes are in the right side, that is right skewed, right is heavy. In such case, we have to bring one node to the left, one node to the left, single left rotation. The tree get balanced. We'll see how and why. Height of C is 0, height of B is minus 1 because there is no left subtree for B, so it is 0. Right subtree is 1 height, so 0 minus 1 is minus 1. For A, there is no left subtree 0, right subtree 2, 0 minus 2 is minus 2. See, the value is not allowed, it is not a valid one. Only 0, 1, minus 1 are allowed values, minus 2 is not the value. Here the tree is in the right side, we have to go for the left rotation. That means where it is violated, in the root node it is violated, in the path from the root node to the node that is inserted. When you get insert that C, here that is violated, you have to bring this A by rotating to the left side. A you have to rotate left side, you have to bring this A left side. B becomes root, A left child, and C right side as usual. B and C not changed. A in the left side of that B. So this here we have to taken one rotation, one left rotation. We'll go for one more case, right rotation. You can see here, you can see here, all the nodes are in the left side, left skewed. Height of this A is 0. The balance factor of B is 1 because 1 minus 0. Balance factor of C is 2 minus 0, that is 2. The node that is violated is C. This is the node. We have to bring that to the right side because left is heavy. You have to go for right rotation, single right rotation. C is rotate to the right side. B is root only. A left child. C becomes the right of B. Now this tree becomes balanced. You can see root the balance factor of A, C are 0. Balance factor of B is height of left subtree minus height of right subtree, 1 minus 1, that is also 0. We'll go for one more case, that is right left right rotation. That means a node is inserted to the right of left subtree. To the C, right now we are following the left side. That new node is inserted to the right of it. New node is inserted to the right of left subtree. As you can say, I will write it here. This is left and this is right for the easy remembering purpose. You have to apply left right rotation. First you go for left rotation, then you go for right rotation. Left rotation, how to do that one? First interchange A and B. B should come here, A should come here. Then you change the direction. Earlier it was in the right side, now bring it to the left side. So B goes above, A will be child, and this is the left link. So once we have rotated, that is till here, it is left rotation. Left rotation is over. As you can see, all the nodes are in the left side. You have to go for the right rotation. See, you should bring to the right side. So that is why it requires two rotation. Once it is left rotation, next it is right rotation. Double rotation is required. Left right rotation. We'll take one more case, that is right left rotation. The balance factor of B is 0. Balance factor of C is 1 because left side is 1, right side is 0. 1 minus 0 is 1. Balance factor of this is 0 minus 2. Left side is 0, right side is 2. That is why it's minus 2. This is the node that is violated. That means the new node is inserted to the left of right subtree. To the left of right subtree. This is right subtree, and to this we have inserted to the left. We have to perform now two rotations, double rotation. First right rotation, then left rotation. We'll go for now right rotation. That is to this node. We'll go for this A later. We have to interchange B and C. We have to interchange B and C. B goes above, C becomes the child. The link now it is in the left side. You have to bring to the right side. So that completes one rotation. Now you can see all the nodes are in the right side. You have to bring that to the left side. A will be rotated to the left side. So this is the balanced tree. We have converted left, we have converted imbalanced tree to the balanced tree by applying two rotations. Now we'll solve one problem. Construct AVL tree for the following data set: 50, 20, 60, 10, 8, 15, 32, 46, 11 and 42. We'll see what kind of rotation is required. There are four rotations: RR rotation, LL rotation, these two single rotation. LR rotation, RL rotation are the double rotation. Now our first data is 50. The BST is empty. There is no root node. 50 becomes the root. Only one node. It is a leaf node. It is a root node. The balance factor is 0. Tree is said to be balanced. Insert 20. 20 is, you have to always start from the root node. You have to start from the root node. Root node is 50. Data to be inserted, the key value is 20. 20 is less than 50. So it should take left side. Then compute, as and when the insertion is done, compute balance factor. Balance factor of 20 is 0. Balance factor of 50 is 1 because left subtree height is 1, right subtree height is 0. 1 minus 0 is 1. 1 is allowed. Tree is balanced. Insert 60. 60 is bigger than the root node value 50. 50 is smaller, 60 is bigger, so it should be in the right side of 50. There is no node in the right side of 50, so node is created that becomes right side, right child of 50. Compute balance factor. Balance factor of 20 is 0. Balance factor of 60 is 0. Balance factor of 50 is left subtree height minus right subtree height. 1 minus 1, that is 0. Tree is balanced. All the nodes not violated, the values that is 0, 1 and minus 1. Now we'll go for inserting the value 10. Start from root 50. 10 is less than 50, should be in the left side. Now there is a left node whose value is 20. Our key value is 10, which is to be inserted. Should be in the left side. There is no left child for 20, insert it. Compute balance factor. 10 is the leaf node, so height is 0. 20, left subtree height is 1, right subtree 0. 1 minus 0, that is 1. Next, 60 is leaf node and height is 0. 50, left subtree height is 2, right subtree height is 1. 2 minus 1 is 1. All the nodes are having balance factor either 0 or 1. So it is a balanced tree. Now we'll go for inserting value 10. Start from root. 8 is less than 50, should be in the left side. 8 is less than 20, should be in the left side. 10 is less than 20. 8 is less than the 10, so it should be in the left of 10. Compute balance factor. For this it is 0. For 10, left subtree height is 1, right subtree height is 0. 1 minus 0 is 1. To 20, left subtree height is 2, right subtree height is 0. 2 minus 0 is 2. So the node that is violated is 20. In the path from the root node to the node that is inserted, you have to come to this part. Okay, pick 3 node. Pick 3 node. I started from here 20 because it is the node where balance factor is violated. In the path of insertion, the 8 is inserted here, so you have to take this path only. So this is in the left, this is in the left. So this requires right rotation. This requires right rotation. That means the 20 has to be rotated to the right. 10 becomes the parent node. 20 20 becomes the right child of 10, 8 as it is. After one's rotation, this is a tree. Now, where to insert the 50? As you know that, as you can see, 10 is less than 50, so it should be the left child. Right side is unchanged. This is the final tree diagram. Now, tree is balanced. You can see the leaf node, this is 0, this is 0, and this is 0. Left subtree 1 minus 1, that is this is also 0, so this is a value which is allowed. Left subtree height is 2 minus 1, that means the balance factor is 1, which is working. Tree is balanced. Go for value 15. The 15 to start always from the root. 15 less left of 50. Okay, 10 already there, it should be the right of 10. Now we are here. 15 less than 20 should be the left of 20. Now compute balance factor. Leaf node 50, so 0. Next 20, left subtree height is 1, right no 0. 1 minus 0 is 1. In this case 10, left subtree height 1, right subtree height 2. 1 minus 2, that is minus 1. For 50, height of left subtree, that is 3. Height of right subtree, that is 1. 3 minus 1, 2. The node that is violated is 2. So you mark that one. So this one, in the path of insertion, you have to select those 3 nodes. Left side, right side. So you have to apply left rotation, then right rotation. Left rotation and then right rotation. For 10, 20, first you have to interchange them. These 3 node you have to rotate it. Okay, how to do that one? First insert the value. Insert the value. That means I will write it here. 10, first the 20 you have to bring it here. 20 you have to bring it there, and 10, 10. Interchange these two values. 20 will go here, 10 will come here. The right link now becomes left link. Right link now becomes left link. Then 50, earlier it was here. Earlier it was here. As you can see, left heavy, left heavy. You have to apply right rotation. That means the 50 you have to rotate it. That means it becomes like this. It becomes like this. 10, 20 and 50. Then where is 60? 60 is right of 50. This is 50. Right of 50 is 60. Then where is that 8? Where is that 8? Where is that 8? 8 is left of 10. Left of 10 is here. 8. Then you have to put 15. 15 is in the left of 20. Left of 20. Okay. Where is that 15? 15 is the right of 10. Right of 10 and left of 15. Both satisfy means this line. This is the part. This is the place. 15 is inserted. So tree get balanced. Dynamically balanced. Insert 32. Always for this, no, the tree having 20 as the root. You start from 20. Our number is 32. 32 is bigger than 20, so should be the right side. Already 50 is there. 50 and 32. 32 should be left of 50. Then compute balance factor. Balance factor of this 4 leaf node are 0. Left subtree minus right subtree 0. Left minus right 0. Left minus right 0. So this tree is balanced. Now the value to be inserted is 46. Start from the root node 20. 46 should be in the right side. Okay. 50. 46 is the left of, if there, should be in the left side. Already 32 is there. 46 is bigger than 32, should be the right side. So insert the node. Compute now balance factor. All the node balance factors are in that range 0, 1, minus 1. So tree is balanced. So no need to balance the tree. Already balanced. Now the value to be inserted is 11. Start from 20. 11 is less than 20, so left side. 10 is there. 11 is bigger than 10, to the right side. 15 is there. 15 and 11. 11 should be the left of 15. So 11 is inserted. Compute the balance factor. As you can see, balance factors are all computed. The values are either 0 or 1 or minus 1. Tree is balanced. Now, the new number to be inserted is 48. Start from 20. 48 should be the right side. Already 50 is there. 48 is less than 50, so should be in the left side. 48 is right side, greater than 32, should be the right side. Already 46 is there. 48 should be the right of 46. There is no node. Insert the node. 48. It comes here. If you compute balance factor, if you compute balance factor, the node that is violating is this one. Mark the 3 nodes in the path from that root to the node that is inserted. These 3 are the node that is violating. You can see right heavy, right heavy. Go for left rotation. Go for left rotation. It is easy. So 46 is a 46, 48, and 32 you have to bring it to the right. It's just a simple single rotation. As right side is heavy, go for left rotation. 32 now becomes the left child of 46. All other nodes are same. You can see 46, 48, 32 are reordered. 50 and the relation between 46. 46 is smaller than 50, should be in the left side. And right child of 50 is not changed, so it is same. So this is the redrawn balanced tree. With this, we have inserted all the given values. You can say that the tree is balanced. Thank you.